Now, one of the things we often want to do is we want to move beyond the firm level, and we want to talk about the industry level or the economy-wide level. So let me talk now about an industry model. And in particular, I'm going to focus on a special case of the industry model, which is the constant returns to scale case. And there are two reasons why the industry model is often tied to the assumption of constant returns to scale. One is, if you're going to assume constant returns to scale, then the firm becomes kind of not a very easily analyzed story, right? Because with constant returns to scale, if the price is above cost, you want to produce an infinite amount. If the price is below cost, you don't want to produce at all. And if the price is equal to cost, you're invariant as to, it's indeterminate what output you want to produce. So kind of the determination of output in that model is fairly difficult. So that's one argument for why, if I'm interested in an industry that has inherently constant returns to scale at the firm level, then when I go to the industry level, I might have to move to the industry to even think about what an equilibrium looks like. I might have to go to the industry level to talk about equilibria, because the equilibrium at the firm level is somewhat indeterminate. Now, the other motivation is, no, at the firm level, we have diminishing returns to scale for some of the reasons we talked about before. That is, eventually the firms run into problem coordinating all of this larger scale, run into various features that cause diminishing returns at the firm level. But at the industry level, we're going to have constant returns to scale because the industry could be composed of lots of optimally sized firms. So each firm might have a U-shaped cost curve, but I can build up my industry by having a bunch of firms in the industry. So even though the firms have diminishing returns after some point, the industry essentially has constant returns because it can replicate the operations. Right? So it's kind of like the grocery business. You might have an optimal size for a grocery store or even a grocery chain, but we can increase the amount of grocery stores, and we could have constant returns to scale by just building more and more stores that are essentially the same. So those are two arguments that get you kind of industry analysis with constant returns to scale. If you start with constant returns to scale, then you're sort of pushed toward the industry as where you're going to find the equilibrium. Or you could say, even if I don't have constant returns to scale at the firm level, I might approximate it at the industry level. So if I'm going to interested in industry, I'm going to assume constant returns to scale. So that's our model. We're going to have constant returns to scale. And I'll do the two-input case to make life relatively easy. And so let's think about when you have constant returns to scale. Everybody knows what constant returns to scale means. What does constant returns to scale mean? Well, at a fundamental level, it says f of t times L and t times k equals t f of L and k. Right? That's what constant returns to scale means, is if I multiply the amount of labor and capital by some proportion, I just get that much more output. So if you make t equal to 2, it says twice as much labor and twice as much capital will produce twice as much output. Right? That could either be what's going on at the firm level, or maybe I'm just duplicating firms to get that same result. Okay? The implications of constant returns to scale in terms of factor demands. Okay? Any ideas? What would be an implication of constant returns to scale production? Any implications? Yeah. So, okay, so a common feature might be that. Okay. So you might say L star of W, R, and Y. This is our conditional factor demand curves. And K star of W, R, and Y. would be something like y times L star of WR and 1 equals y times K star of WR and 1, right? That is the factor demands are just proportional to output. If I want to produce twice as much output, I use twice as much of everything, right? Okay. And also, if a function is homogeneous of degree 1, which is this one is, what's true about its derivatives? Homogeneous of degree 0. So FL of L TL TK equals FL of L and K, right? That is, the marginal product of labor is the same as I move out along a ray. And same is true for the marginal product of capital. Effectively, what's going on, if you think about it in terms of the isoquants of the production function, is that if I look at the unit isoquant, this is F of L and K equals 1. So those are all the combinations of output that produce 1 unit of output. And I go out along a ray, you just double this distance at each point. Right? This would be F of L and K equals 2. If I've just doubled the distance at each point, I'm not sure I drew that exactly right, but if I doubled each of those distances, I would get the 2 unit isoquant, right? All the isoquants are just radial blow-ups of one another. Effectively, once I know the unit isoquant, I know all the isoquants, once I have constant returns to scale. Okay? These conditions here tell us that the slope of the isoquants are the same as I move out, right? That is, the slope here is the same as the slope there. Slope here is the same as the slope there, and the like. Not just the slopes are, but actually the 2 marginal products are the same. So the slopes are clearly the same because both the numerator and the denominator that determine that slope are staying constant as I move out along that ray. Okay? In terms of the cost function, what does the cost function with constant returns to scale look like? C of W, R, and Y. What does it look like? How can you look at a cost function and say, oh, constant returns to scale? What will it always look like? How about this? Y, C of W, R, and 1, right? It'll always look like that. It'll always be Y times something that depends on W and R, okay? Where this is the unit cost function. That's what it costs to produce 1 unit of output, okay? So constant returns to scale is greatly simplifying, okay? It tells me that, for example, I can just, basically you have 2 notions of, there are 2 determinants of factor demand. One is relative prices are going to determine your ratio of K to L. And then the level of output is going to determine how much of each factor you use, right? It has a very nice decomposition between relative prices, which affect relative factor uses, and the level of output, which just increases everything. So what does our constant returns to scale model of the industry look like? Well, you can think about it as, well, what determines output then? What determines output? How are we going to determine output? Well, let's think about it. What are the equilibrium conditions for my industry? Well, if it's a competitive industry, I have to have price equals marginal cost, right? Everybody agrees with that, right? Everybody agrees? Okay. All right. So what is that? Well, how do we think about that equation? P equals Cy of W, R, and Y, which of course is also equal to C of W, R, and 1. Either way you want to think about it, which immediately tells us we have zero profit, right? Zero profit in this world. Okay. What else? What equilibrium conditions do we have? Yeah. Market clearing, which would be Y equals D of P, right? That is, the amount that we're producing has to be equal to the amount that consumers demand for this industry at that price, right? That is, tell me what the equilibrium price is. That determines demand in here. So think of it this way. I got Y and P. I got some demand curve. I got C of W, R, and 1. So factor prices determine unit cost. Once I know unit cost, I know the price. Once I know the price, I know the quantity. Right? That's my equilibrium condition, right? All right. So you kind of see when a constant returns to scale industry, the dichotomy. Basically, input cost determines the price. And once I've determined the price, demand determines output. So you can think about the world in terms of supply and demand, but because supply is perfectly elastic in this world, basically suppliers determine the price, and then given that price, demanders determine the quantity. Okay? And I think for a lot of industries, that's how you want to think about the world. You want to think that prices are mostly going to be determined on the supply side by what it costs to produce the product. And ultimately, the quantity we consume is going to be determined mostly on the demand side by how many consumers want to buy at that price. Okay? All right. So this is a useful model for thinking about many industries, kind of a cost-based approach. And this is an important point. This is a footnote. And a footnote that I don't think we've talked about yet this quarter is, we might as well do it now. Now's as good a time as any. Let's see I see a market. And I see this point. And I see this point. Did we talk about this? We done this? Here's quantity and here's price. This is like embarrassing. This is like Econ 0 or something. This is like Econ 0. To be doing this in a graduate course is somewhat embarrassing, but I'll do it anyway. So this is quantity and price, and these are 2 points, okay? Maybe this is 2014 and 2015. All right? And I want to think about this in terms of supply and demand. Okay? Did we do this? I can't remember. No? All right. All right. So tell me what happened. Yeah. Yeah, well, but I want to actually emphasize a different part of it, which is important to realize. So, if I want to look at this picture, and let's think about this distance here, call this distance delta Q, and call this difference delta P. All right? Those are, think about those measured in percentage changes or log changes, right? So delta Q equals log of Q 2015 minus log of Q 2014, and delta P equals log of P 2015 minus log of Q 20 on P 2014. Okay, so that's my picture. And I want to think about this in terms of changes in supply and demand. That is, how much did demand or supply change between 2014 and 2015? how would we translate these observed changes in prices and quantity into what happened in terms of supply and demand? What can you say? Anybody got? Oh, you all took Econ 0, right? Pretty much, yeah. Okay. So assuming we have downward sloping demand, let's call it delta D is positive. Demand went up, right? Not just it moved to the right. Okay? Anybody be more precise than that? How much did the demand curve move? At a minimum, right? At a minimum. That is, whatever the demand curve did, whatever the demand curve was that went through that, right? Everybody agrees there was a demand curve that went through here. I don't see it, but I know it goes through that point. Everybody. That's the first thing to realize. The first thing to realize, and this is very different than the instrumental variables point. The point is, these points have to be in equilibrium, not just of supply and demand. They have to be an equilibrium for the demanders, and they have to be an equilibrium for the suppliers. So if I only, let's assume I forgot half of economics and only knew demand, that's all I knew, I would still know that there was a demand curve that went through this point, and in 2015, there was a different demand curve that went through that point. Everybody agrees with that, right? Without ever talking about supply. Regardless of monopoly, I don't care, whatever you want to say on the supply side, I know that there was a demand curve that went through that point because that's how it was in equilibrium. And there was a demand curve that went through that point because that's how that was the equilibrium. Correct? For sure, right? People forget that. They think, well, I got to know what happened to supply in order to, no. Those points have to be consistent with whatever happened to demand. So immediately, whether I measure it as this shift here or I measure it as this shift here, that is, if I measure it by how much the demand curve shifted at the old price or how much the demand curve shifted at the new price, in either case, I'm going to say delta D has to be bigger than delta Q. Everybody agree with that? Okay. Now, what about the supply side? If I have an upward sloping supply curve, then what must be true? Well, actually, for the same logic, I can prove delta S has to be less than delta Q, right? For the same reason. Just draw the same picture. That is, I got this point and this point. I got some supply curves. Now, it's true, I don't even know which way supply shifted, but it could not have shifted out. Just draw this supply curve however you want. Make it steep. It couldn't shift out past here. The new demand supply curve, as long as it's upward sloping, has to come into the left of here, and the old one was here. Right? So what I know is delta D bigger than delta Q bigger than delta S. Now, how do I know that? Well, that's all because delta P is positive. If delta P is positive, then I know demand went up more than supply, and therefore they each split where the quantity shows up. If delta P was negative, then I know delta S is bigger than delta Q, bigger than delta D. All right, just goes the other way. All right. So that's an important thing to realize. There's actually a fair amount of information in that price quantity graph about what's happening in this marketplace. Okay? Another way to think about it is think about the following. On the demand side, I know delta Q is delta D plus the elasticity of demand times delta P. Everybody agrees with that? That is, the change in quantity I see consists of some shift in the demand curve and then some movement along the demand curve. Right? That's all there is. Similarly, delta Q equals delta S plus epsilon S delta P. So in fact, this implies delta D equals delta Q minus epsilon D delta P, and delta S equals delta Q minus epsilon S delta P. Okay? So we could back out. If we knew the elasticities, we wouldn't just have these inequalities. We could actually back out what the changes in supply and demand had to be if we knew the two elasticities. Okay? That's the basics of how you look at a market in terms of output, quantity and price changes. Okay? Now you can solve these two equations by setting them equal to each other. You get delta D equals delta D plus epsilon D delta P equals delta S plus epsilon S delta P. That implies delta P equals epsilon S minus epsilon, delta D minus delta S divided by epsilon S minus epsilon D. So that's our standard formula we get in economics that tells us the change in price depends on the increase in demand minus the increase in supply. So it's the growth in excess demand divided by basically the sum of the two elasticities, right? Because the epsilon D is negative. So it's basically the sum of the two elasticities. All right. All right. Any questions that people have about that? And then you can just plug that back in to get delta Q. You plug it into either demand equation to delta Q. Delta Q is then, anybody know what the formula for delta Q is? Actually turns out to be epsilon S delta D minus epsilon D delta S divided by epsilon S minus epsilon D. And now that looks like it's a difference. It's really an average, right? That is, the change in quantity is a weighted average of the change in demand and the change in supply. That's why it's always in the middle, right? Because these numerator weights, remember, this minus epsilon D is a positive number. So these are just like 3 times this plus 1 times that divided by 4. Like 3/4 of one and 1/4 of the other. All right? You can just get that formula by just plugging this into here or plugging it into here. All right, everybody knows this stuff, right? Yes? Should. But it is kind of, do they teach this undergraduate econ? They don't? Why not? What? I got their diploma in the wrong place. Okay. All right, so that's the model. That's the model. That's basic supply and demand. We're not even going to use that whole thing, but that's a footnote to our lecture today. All right, any questions before we move? What else do I need? Well, I need L. L equals CW of W, R, and Y. Everybody agrees with that? And I need K equals CR of W, R, and Y. Okay? All right. And I think that's it. Okay, that's all I need. Oh, no. I need number 4, which is Y equals F of L and K. Right? I need output to be equal to the amount that's, I need labor and capital sufficient to produce the equilibrium amount of output. So what I'm going to do is, just like I did over here, think about changes. I'm going to explain this system in terms of changes. Okay? I want you to think about this as price equals marginal cost. This is output market equilibrium. This is cost minimization. And this is the production function. So my industry model is going to have four ingredients. It's got competitive pricing, price equals marginal cost. It's got an output market equilibrium that says whatever that price is, it's got to be consistent with the level of output that consumers demand. I got to have my firms maximizing profits, which corresponds to minimizing cost. And I got to satisfy my production function. All right. So let's think about what each of these mean in terms of percentage changes in the variables of interest. Okay? All right. So let's think about perturbing this equation. I'm going to get delta P equal to what? What's delta P with constant returns to scale? Delta P has to be equal to what? In terms of the change in W and R. What? Be 0? If W and R are changing, let's assume W and R are changing exactly. I want to study factor demand. How would this industry respond to changes in WR? What would be true in the competitive industry about how output prices would move? Well, they got to move with marginal cost. How is marginal cost affected by changes in W and R? Anybody know? Well, no. Let's just go. Okay. All right. Okay, so let's think about it. Well, what's our equation? P equals Cy of WR and, or C of WR and 1. Everybody agrees with that? Yes? Agrees. So dP equals CW of WR and 1 times dW plus CR WR and 1 dr. Everybody agrees with that? Yes, no, maybe so, right? That's usual trick. Just totally differentiate the equilibrium condition, right? My equilibrium condition is price equal to unit cost. All right? So, what's CW of WR and 1? That's the amount of output, amount of labor you use to produce 1 unit of output. Because we have constant returns to scale, that's just L over Y, right? It's labor per unit output times dW plus K over Y dr. Okay, we're getting close. I want to make these into percentage changes. What do? Divide that by W. I want to put a W there. Divide that by P. I put a P here. Do the same for R. And so what is it? Delta P equals, right? That's a percentage change in P. That's delta P. Has to be equal to share of labor, delta W, plus the share of capital, delta R. Exactly. That is, the change in the price of output is just a share weighted average of the change in input prices. Everybody understand that? So that's going to be my first equation, equation number 1. Delta P equals SL delta W plus SK delta R. That's going to tell me that if input prices change, or drive it the other way, output prices change, my input prices, they have to satisfy this relationship to stick with this price equals marginal cost equilibrium, right? As long as I have price equals marginal cost, I got to obey that equation. As wages and prices move, I got to satisfy that equation. Okay? It's a very simple equation. This, of course, depends on constant return. You can see I used constant returns to scale to get that. What about number 2? What's equation number 2 expressed as changes? How about if I'm going to hold demand fixed, I get delta Y equals epsilon D delta P, right? That is, the change in output is going to have to be equal to the elasticity of demand times the change in the price of the product. That is, consumers are just going to move along their demand curve as product prices move. If you want to have a shift in demand, just add delta D to that if you want. But right now I'm doing it with demand fixed. What about equation 4? I'll skip to 4. How are we going to fill out equation 4? Any idea on equation 4? What's the production function expressed in changes? Well, how do you think we're going to do it? We only know one way, right? Y equals F of L and K. dy equals FL dL plus FK dk, right? Everybody agrees with that, right? Now what do we do? Well, I want to make a percent changes, so dy over y equals FL over y times L dL over L plus Fk times K over y dk over K. What's this? What's LFL over y? Well, we put a P here, and a P here, and a P here, and a P here. Yep, that's SL delta L plus SK delta K. So the change in output is a weighted average of the changes in input quantities. All right, so that's going to be my equation 4. Delta Y equals SL delta L plus SK delta K. So I've gone a long ways to describing my equilibrium. I just need one more equation that'll satisfy equation 3. What's missing so far? What ingredient? You should be able to guess what's missing. What's the piece that I haven't described yet? I've described how input costs affect price. I've described how price affects output. And I've described how inputs have to change to produce the output. What piece of the economic equilibrium in this industry is missing? Yeah, any notion of cost minimization is missing here, right? That is, the idea that the firms are choosing L and K to minimize cost, while implicit in these other equations, I haven't explicitly expressed here. I haven't captured that. Economists measure substitution in the two-factor case using a concept known as the elasticity of substitution. Usually you use the letter sigma. It measures how much factor inputs respond to changes in factor prices along that isoquant, right? Draw the isoquant and ask how do inputs change as we change output. As we change factor prices. Now, the nice thing is with constant returns to scale is all the isoquants look the same as long as I'm moving along a ray. Right? As long as I'm holding either factor ratios constant or factor price ratios constant, same story. As long as I move out along that ray, I'm going to get the same elasticity of substitution with CRS. There's no change in the elasticity of substitution. So we're going to think of the elasticity of substitution as delta L over K equals sigma R over W. And this is where economists, I made it little r, big R, doesn't matter. That's a rental rate of capital. So this delta L over K equals sigma times delta R over W. And there's a little trick in this formula that on the left-hand side I got L over K, and on the right-hand side I have R over W. That just means sigma is going to be positive. That's the trick economists did to make sigma positive. Because there's really a negative relationship between factor prices and factor price ratios and quantity ratios, because demand slopes down. But we define the elasticity of substitution as the change in the factor ratio as a percentage of the change in the factor price ratio measured the opposite way. So if a 10% increase in R over W leads to a 5% change in L over K, we would give you elasticity of substitution of a half. So for some well-known production functions like Cobb-Douglas corresponds to sigma equals 1. Right? Cobb-Douglas is sigma equals 1. Okay, that's the elasticity of substitution. And many things in economics are going to turn on whether that number is bigger or less than 1. One's a nice dividing line. Okay? So in terms of my notation, this implies delta L minus delta K, which is delta L over K, equals sigma delta R minus delta W. That's going to be my equation 3. Delta L minus delta K equals sigma delta R minus delta W. And you notice again, I got L minus K on this side and R minus W on that side. I've done that same flip, where I'm measuring labor to capital on the left and capital labor on the right. Okay? So those 4 equations are really useful for all kinds of equilibrium problems in the two-sector world. You can describe any kind of effect that you might think of. Okay? So for example, we could think about what does the industry elasticity of demand for labor look like? Okay? How would we describe the industry elasticity of demand for labor? How would we use those 4 equations to describe the industry elasticity of demand for labor? Yeah, with respect to the wage. That's what we mean by that. Whenever economists just say the elasticity, they always mean the own price elasticity. Whenever we're talking about cross-price elasticity, we'll refer to a cross-price. So whenever anybody's saying the elasticity of demand, we usually mean own price, but that's correct. What is the industry elasticity of demand for labor with respect to the wage? How would we use these equations to solve it? Well, first off, you got to ask, well, what's going on with capital? What are we assuming about capital? What's the most typical assumption we make when studying demand for one item? We hold the other prices constant. So let's do that one first. So let's set delta R equals 0, which you might think of in our prior discussion. That might be what you call the long run. Capital's variable here. You freely vary capital as much as you want at the same price. Call this long run. Okay? So our 4 equations become delta P equals what? What does my first equation become? SL delta W. Delta Y equals epsilon D delta P. Left-hand equation becomes delta L minus delta K equals minus sigma delta W. And my last equation is still the same as it was. Delta Y equals SL delta L plus SK delta K. All right, those are my 4 equations. How many unknowns do I have? I got to determine what? What's going to change as I change the wage rate? Well, out price is going to change, output's going to change, and labor and capital. So I got the right number of equations and the right number of unknowns. Okay? Let's put these 2 equations together. What do we get? We get delta Y equals SL epsilon D delta W. So it's easy to get the change in output right off of there. That is, the change in output is going to be, well, the wage goes up 10%, labor share is 0.6, so the costs go up 6%, whatever that elasticity of demand is, say it's minus 2, output's going to go down 12%. Right? So people see that? This is what we call the scale effect. That is, in this industry, there's going to be less output. Why is there less output? There's less output because labor costs went up. That's going to raise product prices. That's going to cause output to fall. Right? So a union comes into this industry, jacks up the wage rate rises, prices of output rise, output's going to fall. That's kind of the idea in mind. Okay? How much? Well, how much it raises the output, how much it lowers output depends on labor share as well as the elasticity of demand. Okay? All right. Any questions that people have? Okay? Okay? Anything before we go forward? How about this equation? Anybody think of a useful way to rewrite that equation? Anybody got an idea how you can rewrite that equation? I've never taught it this way, but I think I see how to do it. What if I were to say, rewrite this equation as delta Y equals delta L plus SK delta K minus delta L. Does that look right? Did I do that right? Right? People understand that equation? That implies delta L equals delta Y plus SK delta L minus delta K. I think I did that right. Did I do that right, Casey? I think that's right. It says the change in labor is going to be that scale effect plus whatever happens because they substitute labor capital for labor. Right? Right? But what is delta L minus delta K? It's minus sigma delta W. Okay? And what is delta Y? Delta Y is what? Well, we already determined delta Y right here. So I get delta L equals epsilon D delta, SL epsilon D delta W plus SK times delta L minus delta K, which is what? What is that? Minus sigma delta W. Okay? So first thing you'll notice that both of these are negative, right? This is a negative number. And this is a negative number. So delta L equals SL epsilon D plus SK minus sigma, whole thing delta W. So that's going to be the elasticity of demand for labor.